All right, so we are finishing up all of topic 4/14 today. So this is 14.2, which is on what we call hybridization. So we're going to kind of go through this together today, and then later this week, you guys will have your review for the test for this whole topic, and then the test will be up on for Friday, okay, and Monday for 8A. So hybridization has to do with the fact that when our nonmetals make these covalent bonds, um, there's actually the orbitals, the s and p orbitals, they actually form these hybrid orbitals, and that's what allows them to make the bonds, and the bonds all be sort of equal, I guess you could say. And so, kind of here at the top, it just says that this is hybridization can help explain some of the molecular geometries, those shapes, but with a lot of things in science, it's limited. And so as we do more research, make more progress, there are other things that can explain the same phenomena. And so, obviously things can change, but for right now, this is the accepted theory with hybrid orbitals. So as I mentioned, it's going to be a mixing of different types of atomic orbitals from the same atom. So it's going to be your s and your p orbitals. So remember that you have one s orbital, and then the p sublevel has 3 orbitals. Okay. And so they will mix and they will form one of these 3 that we're going to see right here. Sp3, where you have an s and 3 of the p orbitals. Sp2, where you have an s and 2 of the p orbitals. And then Sp, where you have an s and then 1 of the p orbitals. And so we will look at what they look like for different compounds. And specifically, we're going to look at these 3. These are 3 different organic compounds. One of them has single bonding, one has double, one has triple. And so each one of them is going to have a different hybridization based on the types of bonds that they make. Okay. And then the other thing that we need to be able to is you need to be able to identify and explain the relationships between a few different things. So the Lewis dot structure for a compound, how many electron domains it has, what its molecular geometry, that's the shape, is, and then what type of hybridization, because each type of hybridization corresponds to a certain number of electron domains, and a lot of times to a particular shape, a particular molecular geometry. So as I mentioned, we're going to be having a mixing of atomic orbitals, and so we form hybrid orbitals. So hybrid is kind of like a mixture of 2 different things. And so as I mentioned, you're going to be having your s and p orbitals. So remember that if you think back to topic 2 with our orbital diagrams, the s's always have 1 orbital, and then the p sublevels always have 3. And so we're going to have a mixture of those, and they're going to either make 2, 3, or 4 hybrid orbitals that can then make bonds and create electron domains. Okay. So the first one we're going to look at is Sp3 hybridization. And so the name kind of tells you what it is. If it's Sp3, you're going to end up with 1 s and 3 p orbitals that are hybridized. So they're no longer 1 s orbitals and then 3 p orbitals. You have 4 orbitals, and they're all considered Sp3. So what happens, and carbon atom is usually the most common example we use, because carbon can make so many different bonds. It can make single bonds, double bonds, and triple bonds. And so it's used as a lot of examples because organic chemistry, organic molecules are all carbon based, and it can do all types of hybridization. So normally, if we just look at the periodic table, we know that carbon has 6 valence electrons, or I'm sorry, 6 electrons total. And so normally, if we start from the bottom of our orbital diagram, we have 1s2, 2s2, and then 2p2. And that's where the ground state, so that's the normal state for a carbon atom. Now, what happens is if it gets excited, one of the one of the electrons here from the 2s is going to jump up to the 2p. Okay, so it jumps up to a little higher energy level. And then what happens is then those 4 orbitals, they sort of come together and they form these 4 hybrid orbitals. So notice that all 4 of them are now written at the same level of energy. And if you look closely, they are, if we were to kind of trace a line kind of horizontally across, so 2s is here, 2p is here, And if you notice the sp3, it's kind of in between. My lines aren't very straight, but the sp3, it's a little bit higher energy than the s orbital by itself, but it's not as high as the p orbitals, okay? That's because it's a hybrid, it's in between them. So that 1s and the 3p orbitals have hybridized, and there's a single electron in each one. This explains why carbon is able to make 4 bonds. And so molecules that do this, the biggest example is methane. Methane is CH4. That's an organic compound. It's got 1 carbon atom, and it's single bonded to 4 different hydrogens. And so if you notice, it's got 4 electron domains. So if we go back up here and look at this orbital diagram, sp3, there's 4 different orbitals, hybridized orbitals here. And that means that when you have a molecule with sp3 hybridization, it is going to have tetrahedral electron domain geometry, because it has to have 4 electron domains, because there are 4 of these hybrid orbitals. Okay, so if we look at all 3 examples here, this first one is methane, and in here it's got 1, 2, 3, 4 electron domains. They're all 4 bonds, so that's a tetrahedral molecular geometry. Now this next one, it's still got 4 electron domains, but 3 of them are bonds, 1 of them is lone pair. So that would be an example of trigonal pyramidal for the molecular geometry. And then the last one here is water. So water has sp3 hybridization because it does have 4 electron domains. It's just that 2 of them are bonds, 2 of them are lone pairs. So this example would be something that has the bent molecular shape. So all of the electrons above have tetrahedral electron domain geometry because all of them have 4 total electron domains. The difference is how many of them are bonding domains versus how many of them are the non-bonding domains or the lone pairs. And so all of these have sp3 hybridization because all of them have 4 electron domains around their central atom. The difference is their molecular geometries or their shapes. Okay, the one with 4 bonds is tetrahedral. The one with 3 bonds and 1 lone pair is trigonal pyramidal. That's the NH3. And then the water with 2 bonds and 2 lone pairs is bent. Okay, so for sp3 hybridization, you can have 3 different molecular geometries or 3 different shapes. Okay, for the other ones we're going to talk about, usually they really only have 1 shape that they fall into. So the second one is sp2. And again, if we look, here's the carbon atom, and then here's the excited state. So those 2 parts look the same as the first example with the sp3. But then what happens is only 2 of the p orbitals form this hybrid. You still have 1 p orbital that's by itself at the normal amount of energy for a p. And the reason for this is because you're usually going to have you can potentially have a double bond. You don't have to have a double bond, but there are only 3 bonds in this hybrid orbital. So that means that these molecules are going to always have trigonal planar electron domain geometry. So they're always going to have 3 electron domains. So if we come down here, this first one is called ethene. So ethene, ETH, if it doesn't have the M, it's just eth. Eth means that it has 2 carbon atoms. So we can see the 2 carbon atoms here. And then the reason it ends in ENE is because it has a double bond. Okay, so the first example when we were back up here, I told you guys that this one was methane. The meth, METH, means there's only 1 carbon atom. And then ANE, that ending means that there's only single bonds in the molecule. There's no double or triple bonds. So the second one down here, ethene, the eth means there's 2 carbon atoms in a chain, and the ENE means that those carbon atoms have a double bond between them. Okay, so ethene is an example of something that does sp2 hybridization, because if I look around the carbon atoms, there's 1, 2, 3 electron domains around that carbon atom, and if I check the other one, it's also 3. 1, 2, 3. So if either carbon atom, they both have 3 electron domains around them. So both of those carbons have sp2 hybridization. An example that's not got carbon, that's not an organic molecule, would be boron trifluoride, this one over here. So the boron's the central atom, and I can see it has 1, 2, 3 electron domains. Okay, so sp2 hybridization, we usually either see that in molecules like ethene, where one of the carbons is double bonded, so then it only has 3 electron domains, or something like boron that doesn't have a full, complete octet. Okay, because normally, remember, to follow the octet rule, everybody's got to have 8 electrons, and so boron is one that defies that rule and it only has 6 usually. And so usually it'll be boron, or it'll be one of these carbon organic molecules where one of the carbons has a double bond, and that's still, so the carbons are still following the octet rule over here because they have 2 singles and 1 double bond, so that's still 8 total electrons around the carbon. But because one of them is consists of a double bond, that gives it the sp2 hybridization. So for sp2 hybridization, they all have 3 electron domains, okay, which means that they all have trigonal planar geometry for both electron domain geometry and for molecular geometry. And so the bond angle on sp2 is always 120 because trigonal planar is the only shape that it can be. Okay, it's not like the sp3 or up here, because they had 4 electron domains, it could have been any of these 3 shapes that actually have slightly different bond angles. Okay. All right, the last one is sp hybridization. So similar concepts, you have your atom and your ground state. So this example is again is carbon. It gets excited, so one of the electrons from the 2s jumps up. And then what happens is you only have the s and one of the p orbitals forming what we call an sp hybrid orbital. Okay, you have 2 of them that stay up in the p orbital. All right, so now since there's only 2 hybrid orbitals in sp, molecules that have sp hybridization, they are only going to be able to have 2 electron domains because they only have 2 hybrid orbitals. So looking at these examples, this first one is called ethine. So it's still eth because it still just has 2 carbon atoms here in the chain. But now instead of ene, it's yne. The reason it's yne is because yne for organic molecules, that means there's a triple bond between the carbons somewhere. Okay. And so I know we haven't gotten to like topic 10 with organic naming yet, but you should start getting used to recognizing if it ends in ane, like the first one was methane. If it ends in ane, that means everything's a single bond. If it ends in ene, that means there's a double bond between some carbons somewhere. And if it's yne, there's a triple bond between the carbons somewhere. And then if it starts with meth, there's only 1 carbon in the chain. If it starts with eth, there's going to be 2 carbons chained together in a bond or bonded together. Okay. This one in the middle, this would be a non-organic example, beryllium chloride or dichloride. The reason, again, beryllium is one of our atoms that defies the octet rule. It only wants to have 4 electrons instead of 8, similar to boron only wanting to have 6. Okay. So for sp hybridization, it's either going to be something with beryllium, or it's going to be something with carbon that does that only has 2 electron domains. So for ethine, the first one on here on the left, this carbon, there's a single bond here, and then it's triple bonded to the other carbon. So that's 2 electron domains. And then the other carbon is the same thing. It's got a single bond here, and it's triple bonded to that one. So both of those carbons are sp hybridized in that ethine molecule. Here, the beryllium chloride, it's got 2 single bonds on the sides of the beryllium, so that's 2 electron domains. And then the other example, that this is a common molecule that you guys should be kind of used to identifying, just like the water was sp3, carbon dioxide is sp2 because it's got 2 double bonds, and so that's just 2 electron domains. Okay, so all of these molecules do sp hybridization, because all of them have 2 electron domains around that atom that's in the center. Okay, and so anytime you have something with sp hybridization, because it only has 2 electron domains, the only electron domain geometry and molecular geometry it can be is linear. And so they're always going to be in a straight line, and they're always going to be 180 degrees. Okay, so that last bullet that I had kind of on the summary before we started was talking about sort of how all these things correspond to each other. So if you are either shown a Lewis structure or you're asked to draw a Lewis structure, once you have the Lewis structure drawn, you should be able to look at it. You should be able to figure out how many electron domains are around the central atom. And then from that, you should be able to figure out what shape it is, what molecular geometry name it is, the bond angles. And then you should now also be able to tell me which hybridization is it? Is it Sp3, Sp2, or is it Sp? Okay. And that, because that corresponds to the number of electron domains that it has. So on your exercises today, you have kind of a table where you're summarizing what we just said. Just remember though, on the 4 electron domains for molecular geometry and bond angle, you'll have multiple answers because that was the one that it could have been 3 different shapes. This one right here, it says describe the hybridization of the carbon atom in ethane, ethine. There's a typo here. It's supposed to be, the second one is supposed to be ethene with an E and E. Ethane, ethene, and ethine. Okay. And so to help you out, because we haven't gotten to organic yet. So I told you guys earlier that Eth means there's 2 carbons. Okay. So all of these are going to have 2 carbons bonded to each other. The difference is ethane, since it ends in A and E, the carbons are single bonded. So it's going to look like what I just what I just drew, I should say. And then in order to complete their octets, each carbon will have 3 hydrogens, because after you bond your carbons, you fill in everything with hydrogens until they have a complete octet. So if your carbons are just single bonded like this, they each have to have 3 hydrogens to give them 4 electron domains and complete their octet of having 8 electrons around them. So that's what ethane would look like. So you can kind of look at the carbons and kind of determine based on the number of electron domains what type of hybridization that would have. For ethene, excuse me, and ethine, those were drawn up on the other examples, but I'll kind of redraw them here. So ethene, the carbons are going to be double bonded. And so since they're double bonded, then they will each only have 2 hydrogens coming off of them, because that double bond, that counts as 2. That's 4 electrons of the octet. So they each only need 2 more bonds to complete their octet and have 8 electrons around them. And then the last one, ethine, because it's Y and E, that means there's triple bonded carbons, and therefore they would each only need 1 more hydrogen to complete their octet. Okay. When we get to next year, because we won't get to it until the fall, but next year when we start looking at organic, you're going to be able to like draw all these organic molecules, know their names, and all that kind of stuff. So this is kind of a preview of that. The last one, it just says determine the hybridization of the atom and the bond angle around the atoms in bold. So make sure that you're looking at the one that's bolded. So you're going to have to do what I was saying earlier. You're going to have to, number 1, draw the Lewis structure. So there's some space on here. If you need to do it on a separate page and then scan it in with your notes separately, that's fine. But if you need more room than what's on here, but you should have the Lewis structure drawn. Okay. Once you have the Lewis structure drawn, you should then be able to look at it, and you should be able to count the number of electron domains around whichever atom is bolded. Okay. And then based on the number of electron domains, you should be able to tell me the molecular geometry, the shape, which will allow you to know the bond angle. And then you should be able to get the hybridization from the number of electron domains as well. Okay. So for example, if I do the letter A, it's H2S. And so if I start out, I have each of the H's have a single electron. The sulfur has 6 because it's in group 16. And so I'm going to end up with the sulfur in the center. It'll be bonded to H's, and it'll still have these 2 lone pairs on it. Okay. So if I look kind of around the sulfur, because that's the one they wanted me to do, there are 4 electron domains. 2 of them are bonds and 2 of them are lone pairs. Okay. So really, if I want to draw it better, it would look like this, because both of the lone pairs would be kind of up here on top. So, but either way, it's got 4 electron domains, 2 bonds, 2 lone pairs. That means that it has an electron domain geometry of tetrahedral, but a molecular geometry of bent, similar to water. And since it's got 4 electron domains, that means this is sp3 hybridized. And since it's bent in the molecular geometry, the bond angle would be less than 109.5. Okay. So that's sort of how you would do that process on this one, is kind of drawing out the structure, looking at the total electron domains, and from that you should be able to figure out the molecular shape and the bond angle, and also the hybridization.